Good, thanks for the invitation, Helena and Alexander. I apologize in advance. This was very short notice. However, yeah, also a little bit of coffee. I usually don't drink coffee before I talk because I'm quite excited, but we have a lot to get through here, so hopefully you can bear with me through this. Yeah, title of the talk is Multi-Band Topological Semimetals. A little bit of nonlinear magnetism, but we will go through fast, and I also skipped through some of the introduction because I expect that you guys know a lot of the background work here. If you don't know, I'm Jacob GAYLES. I just started a position as assistant professor at University of South Florida, and we recently combined 3 different universities together, which is all over Florida. I'll show you actually where this work. There we go. Yeah, so it's not actually in South Florida, it's actually in the central Florida here. So this is where I am. We combined also with St. Petersburg, which is about 30 minutes away, and Sarasota. And then between here, where I am, is Miami and the Everglades. So that's why they call it South Florida, because essentially there's not much here, but alligators and swamp. If you have questions, you can email me or look it up. Let's see, is it working? Okay, yeah. Some of the collaborators, so this is over some time, and some different works, and I'll go through it now. Let's see. There we go. My current group, my postdoc, who's done some of the work here, this guy actually left for experiment because he said it was a bit more interesting. And then my graduate student, who's actually here in Mainz today, and undergraduate, and another undergraduate. Does it work? Oh, okay. Ooh, did it work? Oh yeah, let's skip this slide because we're gonna go quite fast, and if it works. All right, yeah, so let's get to the main topic. I like stories that, you know, kind of spoil the end. So I'm gonna tell you the results before we actually get into the discussion of it. What we're looking at is 3 different materials here. One is this X, which is a transition metal, and platinum is a cubic system. Then we also have we have manganese and bismuth, which is hexagonal, and then we also have this potassium, vanadium, antimony, which is this kagome layered material. And what's interesting about them is that they have very complicated band structures. And if this works, they have very complicated band structures. This is actually the DFT calculation by Libor, but they have very interesting band structures here, and that they're very complicated. They don't have, you know, these 2 bands crossings like we usually see in many materials. And if it works. So one of the results is in potassium, vanadium, antimony, where we saw this very large linear anomalous Hall effect on a log scale of the conductivity and anomalous Hall effect. And we'll get into that, and that's quite nice because it's quite different from what we usually expect in this scaling of the anomalous Hall effect. And the next one is this chromium platinum 3, which shows also a larger anomalous Hall effect compared to this cobalt 310 and cobalt 2 manganese gallium in the intrinsic regime. And then lastly, we have this manganese bismuth, which has, for a magnetic material, a very high mobility compared to many of the well-known wild semimetals and other materials that are well-known. So that's the spoiler, and let's get into it if this works. So, is there a timer somewhere also? Yeah, or are you doing the timer? Okay, yeah. So maybe we go over 20 minutes of it, sorry. The outline, we'll discuss the anomalous Hall effect in different regimes, and then we'll go over a simple model with these multiple bands, and then I think we're gonna end here on this cubic platinum 3 compound. And if you guys have more questions, we can talk about it over lunch on the other compounds. All right, so anomalous Hall effect in different regimes. This is a very well-known picture. We usually talk about it in semi-classical case because it's a bit easier to understand. And so what you have here, we have 3 different regimes. I'm just gonna use my clicker here. So we have this one case, which is the skew scattering regime, which is shown here to the right. And this is usually in the case with very large conductivity. And what happens is essentially, this is like a Mott scattering, where the electrons find some potential, and based on their spin, they scatter in different directions, yeah? And this is the case for the potassium, vanadium, antimony. However, what was interesting about this, not that it was large, but it was a new mechanism. Do I have it? Yeah, for scattering, yeah? So usually we think of this scattering for instance, in iron, where it's a very clean limit, you have a very small amount of scatterers to produce this skew scattering result. Or you can think of the opposite regime where you have this dilute condo type system where you have a single magnetic scatterer that can also produce this. And in this case, the potassium, vanadium, antimony was grown quite clean by the experimentalists. However, what you have is this magnetic texture from this Kagome net, and this the magnetic structure here actually acts as a scattering. So you remove that condition for an impurity scatterer, but they're replacing it with this potential of this magnetic Kagome net. That's the system there, and it actually got some very nice results here. This is the RPES along with the DOT results. And then let's continue to the next case. The next case is very well known. This is called the intrinsic deflection, which is due to this Berry curvature in the system, and this is completely due to the band structure here, where the band structure will actually accelerate the electrons based on the anti-crossings in the system. And then lastly is the regime that we don't really talk much about, but it's a side jump scattering where you add a phase shift to your spin based on an impurity. The last two are shown in blue because they're independent of the number of, or the density of impurities. And you can separate these quite easily experimentally. Okay, so let's go to the next case, right? So here, and what's the time at the moment? Okay. All right. So yeah, here we start with a simple Hamiltonian here, where we have some spin orbit term. This is linear in k when you have small k, due to the sign here. When you take this, if you expand the sign here, you have some exchange field here, and then you have the hopping that's quite general, which is squared in this case. And then this is also all the spin dependent here. What you get is actually, you get different type, and the simplest case here, you get a chiral band. When you look at the anomalous Hall effect, at that crossing, you get maximized at the crossing, yeah? And I can easily, play with these parameters. If I want to change the sign, I have to play with two of them simultaneously, then I can invert the sign of this anomalous Hall effect. Is that okay? So the next step that I can make is that I can bring two of those Hamiltonians together and couple them. And essentially what will happen is I get two different cases. One case is if I change the chirality for one of the Hamiltonians, I will essentially decrease the size of my anomalous Hall effect. Okay? And then I can also bring it together with the same chirality and essentially double the size of my anomalous Hall effect, yeah? So let's see. For the single band crossing, we have this case of cobalt 310, which is this very popular wild semi-metal, which has exactly 2 wild points in the beryllium zone, in the first beryllium zone, and it has anomalous Hall effect that maxes out about 1,000. Also for the cobalt 2 manganese gallium, which I think Helena has worked a lot with here, and also which has a large Nernst effect because this is also spin, orbit, heat, and transport and magnets, right? So this is, Helena has worked a lot with, which also has exactly those 2 crossing points in the band structure. And what's interesting here is you can also, in terms of these materials, you can thin them down to small layers and you produce a quantum anomalous Hall effect depending on how you terminate them. And then the next thing we went to was this, which, because I worked in Collier Fezer's group, we worked with hoisters a lot, and so we went to this cobalt 2 titanium 10, which we expected to have a very large Berry curvature because it had a lot of wild points at the center. And what happened was the Berry curvature was actually quite small. And what happened here was the combination of different chiralities that essentially canceled out the Berry curvature. So it was not very interesting, PRB, and we moved on. So let's move to the cubic XPT3 compounds. So this is actually a well-known compound for magneto-optic recording back in the 90s. And so this X's can be replaced by vanadium, chromium, or manganese, and we did some calculations just to make sure the magnetic moment and things are operating properly. What's also interesting about this compound, although it's cubic, the magnetic symmetry actually differentiates these side platinum atoms from the top ones, which makes it actually tetragonal symmetry in the end. So let's go back and review the three hot compounds there. So we have cobalt-310, we have the cobalt-2 manganese gallium, both with very simple band structures, and then lastly we have the chromium platinum-3 with a very complicated band structure. And the goal here was, how do we disentangle that to get something similar to these two? So one, we did a Berry curvature calculation, of course. In this case, we were able to separate the band structure into two bands that give the primary Berry curvature. And here what we show is the band structure for the red and blue, this set of red and blue bands, and a set of blue bands instead of red bands. And what you can see is here is a contribution to the anomalous Hall effect from those bands. The dashed line here, which you can barely see, and you'll see it in the next graph, is the result from all other bands. And that's for the vanadium platinum, this is for the chromium platinum, and then lastly is the manganese platinum 3. And then I'm going to continue here a little bit faster. So we also found that with the large anomalous Hall effect also comes a large anomalous Nernst effect. And we can exactly find these bands. This is the nodal lines with those bands without spin-over coupling. And then once we add spin-over coupling, essentially those bands gap. And here what we can see from those red bands that we have the wild points that pop up and also two nodal lines that pop up due to that tetragonal symmetry for both the red and blue. And so to make it more interesting, we said, okay, yeah, this is tetragonal symmetry here, so let's strain it and see how that actually affects the wild points and the nodal lines. So we did several types of strain. One is we did a tetragonal strain, and we also did a rhombohedral strain, or what I would call a hexagonal strain, but it's not a hexagonal symmetry. So my postdoc here looked at this, where she looked at the anomalous Hall effect for all these different phases, and one thing that you see is that going from the cubic to the tetragonal, you actually increase the size of the anomalous Hall effect drastically. And then in the case of the hexagonal and the rhombohedral, you decrease it due to the reduction of the wild points and the nodal lines. And then you can also see that actually the increase and decrease, how the number of wild points actually decreases as you go from cubic to tetragonal to hexagonal to this rhombohedral. I actually should not call this hexagonal because it's not 60 degrees. And then also what we have here is actually work done by my undergraduate student where he actually looked at the anisotropy for the different cases. So this, of course, is the cubic here, which I think everyone will see quite easily, which has a very low anisotropy compared to the tetragonal, which has this easy plane. And here, I think the hexagonal is actually incorrect at the moment, but we need to add a few more extra terms for this, and then here's the rhombohedral. Oh, no, they're not. So, sorry, yeah, let me explain that real quick. The wild points are a bit more complicated to plot because there's so many of them. But if you look at the nodal lines, the color of the nodal lines tells you where it is in relation to the Fermi energy. So we're still trying to figure out how to plot, 50, 60 wild points with respect to the Fermi energy. It gets kind of confusing. So the experimental results. So Anastasios Marco made some thin films of this. He made two different versions, essentially because we wanted to see what the amount of chromium content, how the anomalous Hall effect behaves, and so we were also able to extract those different contributions. Here, the skew scattering contribution, and then we add both the intrinsic and side jump together in this case. And so I forget the actual composition of these two. I think I deleted that slide. And so then here's, that result I showed earlier. So here's the ab initio calculation, and here the red is the red goes to here, and the blue goes to here, and it matches actually quite well. In this case, you see the cobalt-310, and here you see the cobalt-2 manganese gallium. I think Helena remembers this curve because there was always some problem with the cobalt-2 manganese gallium there. And you can see that there because it has very weird dependence. And these are all single thin films here that we compare to, but in a single crystal case, it does actually become flat. And essentially, as you go to the elemental metals like iron, gadolinium, nickel, and cobalt, you have this very flat intrinsic dependence, and then as you get to a very high conductivity, they start to become skew scattering, as explained. So what happens here is actually quite interesting because essentially, this low conductivity side is the wild metals, of course, right? Because you have these very few density of states, you have this linear crossing, And on the right side, you have these very metallic systems with lots of bands, which are, higher conductivity here, but they are intrinsic in a sense, but quite lower than the topological cases. And then right in the middle is this case of chromium platinum 3, where you have these 4 sets of bands that we showed, and this is a log plot also, so you have a double the size in the anomalous Hall effect. That's it again, in a bigger form, if you guys couldn't see before. And how much time we have now? Okay, we can quickly go over this. So the next material is this manganese bismuth, which was essentially what we wanted to do is combine magnetic textures with this wow effect. Yeah? And so this idea is that we have this essential fight between 2 different topologies, right? And the reason why we chose manganese bismuth was one is manganese has this half filling, and bismuth has a lot of spin over coupling. So usually you see in almost all topological materials, you see bismuth, and all skyrmion type materials, you see manganese, yeah? And so, of course, I think you guys all know what the skyrmions are. Does anyone need a review on that? No. Those are the different types of skyrmions that are allowed, 2-dimensional skyrmions in this case. And of course, this comes out of this Barry's physics, where you essentially add a phase to your electron and transport. I'll go over real quick. So this is me actually like 15 years ago. And this is actually a point in my life where I wasn't sure that I wanted to do physics essentially. But this was a Saturday morning actually, and I was essentially very interested in magnetism at this time, but I didn't like classes. And so essentially what I'm doing here is I have a Hall probe, and this is my first experiment, by the way, Helena, and my last one. But essentially I'm measuring the magnetic field in and outside of a solenoid, and Helena's like, Jacob, this is a very easy answer. It's constant inside and 0 outside, yeah? Correct?
Yeah. Can I feel, is this Mr. Barry?
No, definitely not. But the one thing here actually that's interesting is that in between going from outside to inside, there's actually a finite magnetic field, and it actually does not drop, discontinuously, yeah? And so this was a small step for me, but I didn't realize it was a big step for my career. And essentially what happens here is that essentially what you have is this solenoid, but you have a vector potential that is not finite outside the magnetic field, right? And this vector potential can have an effect, right? And so essentially it will create, if you send a beam of electrons, split them up, you create an interference pattern on the other side, which is called the Aronoff-Bohm effect. And so that's what happens with skyrmions. Skyrmions are these essentially these solenoids in materials. And the one problem was with this manganese bismuth, we didn't get skyrmions. We actually got what some people will call skyrmion bubbles. So they were quite large. They have more of a constant magnetic field in between. And we were able to calculate this and also find this experimentally. So this is some of the experimental results where in the bulk, you don't see these skyrmions, but when you start to, or these bubbles, when you start to thin it down in the microsized devices, you actually get this very distinct topological Hall effect that's away from 0. And let's continue. Yeah, and then we also image those with LTM, those are the bubbles there, directly imaged with people in Dresden. And we were able to get a phase diagram out of this. I'm going to kind of speed up here. And then we also were able to look at the RPEs and get the band structure for those materials. And then lastly, this was the last earlier spoiler I gave, where this manganese bismuth has actually a very high mobility, and these high mobilities are very indicative of linear crossings in the bands. And you compare this to also this cobalt-310 and this cobalt-2 manganese gallium, which actually have a much lower mobility compared to this. This is, going from less than 1,000 to 5,000 quite fast, and this is really due to that multiple set of bands that we discussed in chromium platinum 3. That's the summary of results. Of course, if you guys know good students, I think everyone here is looking for good students, but if you know good students, send them to me. And that's the USF building. The references, I can send the slides if you like, and that's my son.